we've got a problem here with a charge. So remember that we do not need two charged particles to have an electric field. To have a force between two particles, you do have, between two things, you need two of them. Again, the last section, we needed Q1 and Q2 because we were finding the force that existed between them. Now what we're doing is finding the field that is apparent because of this single charge in space. So it's pretty much like you have some, it's like you have some charged sphere, okay, with a charge of 10 microcoulombs. Okay? Can't what, guys?
You should see my notes.
Oh, circles are tough to draw, yeah. You can use, there's some programs that photo shapes in them. I would use those probably. Anyhow, remember from yesterday, field lines from a positive charge always come out. So we can start by drawing an image of the field around this charge. So we've got some charged sphere in space, and it has field lines coming out of it. Now, we're told to determine the electric field at a point that's 10 centimeters from the charge. So let's list our givens. Our Q value is 10 times 10 to the negative 6 coulombs. Okay, why 10 to the negative 6? Because it's microcoulombs. The R value is 0.1 meters.
Yeah, are we allowed to write that? I've been doing that. Is that okay if we do the calculator for them?
Your answer should always have times 10 to the in the answer. You can go through all the steps like that, but your final answer should say times 10 to the 7 or times 10 to the 8.
You didn't take off on a brown scissors,
right? I honestly don't remember it. That's yeah. We'll see how he grades that one. I'll take a look. But Jeff, in the future, you should definitely never write with the capital E. You should write times 10 to the. Okay?
I've always been writing it with
and you never lost points on it probably yet? Yeah, but just for your future, you should definitely not use the E notation.
Why not?
It's just not standardized, yeah. That's for calculator notation only. It's not something you write down that way. Little e is the natural log base, so it may get confused there. I know it's capital, so it doesn't matter. Yeah, I said little e, yeah. All right. Then determine the electric force felt. Okay, so we're going to have to find electric force, and then we're going to talk about whether this force is attractive or repulsive. So first, start with your equation from yesterday. The electric field produced, okay, the first equation we had is the force over some test charge. But we don't know anything about a test charge yet. All we know is the actual charge and the distance away, so we can't use this formula just yet. So let's just put it on the side for now. Okay, leave it on the side. Our other formula we had, and you'll be given both of these, was KC Q over R squared. And that's the one that we do know. Because we know Q, we know R, KC is a constant, so we can find the electric field, okay, because of that. So we're determining the electric field at a point 10 centimeters away. So we're doing this part first.
KC is 9 times 10 to the 9.
Okay, that's what we're doing right now. So KC is 9 times 10 to the 9 Newton meters squared per Coulomb squared. Okay? So let's go ahead and plug in.
99, 10,
times the 9. Oh yeah, that's the case.
Okay. Is what?
No.
Dan?
Is that an F or force? Both points then?
R. Distance between? Notice I carry all my units down. Okay, in the first substitution, try and get used to that. Okay, afterward you can drop units, but try and get used to putting units in the first one. So we plugged in our Q and our R value into the formula. What will this yield? Who's got a number for me? You should all be checking, as always. When it comes to the test, and people ask me, how do I plug this in? I'm going to be like, really? Really?
I found my calculator as well.
Found it? Good.
My calculator for a good month and a half. You didn't tell me. And you didn't know. I didn't even know I wasn't using it. So I was using like some ghetto calculator.
I saw the one you were using that time, the 4 function.
Yeah.
90,000.
What do you got?
100,000.
900,000? Okay, which we'll write as, for the sake of scientific notation, 9 times 10 to the 5th. Now, electric field, remember, is measured in newtons per coulomb. Okay, newtons per coulomb. So, the force felt in the next part that we have to determine, it says, imagine now there's an electron at this location. What would the force felt be? So, here's the deal. Here's what's going on. We don't want to go through the force formula. There's no need to go ahead and write out the whole force formula and solve for Fe. We can use up here what we see. Okay, we know the force, we know the electric field, E. We know the test charge, because now, instead of it being a positive test charge, we know that it happens to be, an electron. So we know what the Q value will be for an electron. Okay, if you remember from that table we looked at. Okay? Yeah, negative 1.6.
Negative 6.
Negative, much bigger number.
Negative
19.
16.
19.
Oh.
Okay? So for part B, what we're going to do is this. We're going to again look at our formula. What we're going to do is we're going to go back and use this formula here. Okay, so let's solve for Fe. Okay, so multiply both sides by Q0 to get Fe. Again, yesterday or 3 days ago, when we solved for Fe, we used K, Q1, Q2 over R squared. There's no need to go through all that math again because we know the electric field. We determined it right here. And we know Q0, that's the charge of an electron. Okay, that's something that we should know, and it's on our formula sheet as well. So if we want to figure out what the force is, we take the electric field, which was given from the previous answer, and we multiply that by a charge on an electron. The charge on an electron is negative 1.6 times 10 to the negative 19 coulombs. So we're just going to multiply these two numbers together. What do we get when we multiply these two numbers together?
Is Q0 always negative 1.6?
By the way, are we sure it was 9 times 10 to the 5th, or was it 6th? It was definitely 900,000 for you? Check your zeros to keep track, please. Good. So when you multiply these two numbers together, what do we get as our result? Not everybody at once. Make sure you check your calculators, people.
Is it really 1.6? Is it negative 1.6? I thought it was 1.6.
Negative 1.6 for an electron, 1.6 for a proton.
Of course. You're the
Negative
best.
1.44 times 10 to the negative 13.
I got that too.
This is the best class ever.
Very good, Jeff.
Negative 1.44.
Yeah, so we were told that it was an electron, so we knew it was a negative charge.
Whoa, I got something completely different.
Well, check your work. Let's take a look.
Pretty sure
5 and negative 19 gives you a negative exponent for sure. Multiplying these comes out to 144.
Negative 9.
The last part of this problem asks, is this an attractive or repulsive force? Attractive or repulsive?
It's attractive because it's a negative answer.
Okay, 1, because it's a negative answer, so it's attractive. That's fine. What's the other way to think about it? The charge in the middle is what? What was the net charge in the beginning part? And what's an electron charge?
Negative.
And they're opposites, right?
So opposites attract.
Opposites attract, so it's an attractive charge or attractive force.
If you look at the force and if it was positive, would it be
Repulsive.
repulsive? Okay.
Except when we have 3 of them, remember, we looked at a free body diagram. Okay, so remember that.
Wait, what's the units for E?
Newtons per coulomb. It's a force per unit charge. That's what the definition is by definition. All right, let's take a look at the next example here. We're doing one more. We have a short period today. We just have one more to go. This formula instead. Oops. Please write. Paul.
Was it attractive or repulsive?
So it's a positive starting charge with an electron means they're going to attract. Because remember the 10 microcoulombs was positive, that sphere we drew?
Oh, yeah.
And then the negative electron means they're opposite, so they attract. So attractive force. Determine the electric field produced by two charges. Two charges of 3 times 10 to the negative 8 coulombs and negative 2 times 10 to the negative 8 coulombs. at a point halfway between them.
Are these on movie yet? These ones?
Look under notes and under 17.3 slides. They are separated by a distance of 40 centimeters. Okay, by 40 centimeters.
This allergy season's killing me.
Yeah.
Feel free to go ahead and draw a picture.
It's gonna be 51 degrees on Sunday.
Let's go streak.
I heard it's gonna snow today and tomorrow.
Keeps man up.
Yeah, then it's gonna be 51 degrees on Sunday.
And then the world's gonna be.
Yo, why don't you get a tan on, Jeff?
Yeah.
Yeah, sure. I don't want to come in this.
Remember here, the distance between them is assumed to be center to center. We don't have to worry about the radii.
Hey, Jeff.
So, notice, I've drawn a point in space in the middle here. This point in space is the location at which we're trying to determine the electric field. The positive charge comes from the 3 times 10 to the negative 8. The negative charge comes from negative 2 times 10 to the negative 8. The distance between them is 40 centimeters.
So
Okay?
0.04 meters.
0.4. 0.4. Remember, 2 spots for centime.
10 cents, negative seconds.
Okay? Now, what we need to think about for this kind of a problem is that we have 2 electric fields overlapping at that point in space. We have an electric field produced from the positive charge and one from the negative charge overlapping in that location. So we need to use our superposition principle that we used the other day. The same thing we talked about with forces, where we found the force from each of them and added them together. So if we want the electric field at that point, we need to find the electric field produced by one of them at that point. So now we're looking at the electric field between these 2 locations here, between the positive charge and the point in space, and the electric field between this, the negative charge and the point in space. So what we're doing here is we're doing 2 of these problems really, and then we're just summing them together. Okay, again, superposition. So what we have is the following. Now, call this Q1, call this R1. And for E2, we can call that Q2 and call that R2. It happens that R2 and R1 are the same, aren't they? What is R2 and what is R1?
No, it's the half of 0.4.
It's point.
Good. It's half of it, so it's
0.4.
0.2. Again, the distance from the center of the positive charge to the point in space is 20 centimeters, and the other distance is 20 centimeters. Please make note of that in your diagram. So in this problem, the only difference in the formula is Q1 and Q2. R1 and R2 are the same. Let's go ahead and plug in.
Jeff, don't make silly mistakes.
Silly.
This is, we're doing a super, I'm a
I'm
little.
in China for the public.
This is the superposition.
Superposition, which simply means we can look at each individual charge or each individual field and just sum them together. So superposition always means, holds true when you can add 2 things together to give a larger result.
And why couldn't we just do AC Q1, Q2?
Because that gives you the force between them. Fe, exactly, exactly.
And why couldn't we do the equation we just used, or E equals Fe over,
Because we don't know Q naught, that's the point in space. We don't know what the charge is, where it is, and we don't know Fe either.
like Q0, right?
Q naught, yeah, Q0. Sorry, I keep saying Q naught. It is Q naught, but also Q0. So please notice the only difference here.
6,750.
Okay, the only difference you're going to see here is that your value for Q's are different.
E1.
That's okay.
That's fine, yeah. Okay, the formulas should look identical besides that. E1, Fernando?
6,750.
Units?
Meters of the fields.
Okay, that's E1. Check your work, please. That is correct. Anybody, E2, anybody different for E2? Somebody different?
No.
Get -1,000
Negative 4,500.
Jeff, thank you.
God damn. Yes. Stop calling out.
So these are the values we get. So here's what's happening right now. At that point, halfway in between them, there's a positive field produced from that positive charge, and there's a negative field produced from the negative charge. So what we can do is simply say the overall field is just the sum of these two quantities. Okay? Well, that's what we're going to talk about now. Hold on. So E is equal to E1 plus E2. So we sum them together.
Isn't the inner charge neutral?
Is the inner charge neutral?
That little point in space?
That point in space is not charged. It's just a point in space. Okay, it's just a point in space. It is not charged. Correct. All right, so that's all we're doing at this point. We're simply summing them together to get a total charge or a total field produced of 2250 newtons per coulomb.
But since they're the opposite charges, wouldn't you sum the absolute values because they're the negative one is to the right, so that it's pulling to the right, and then the positive one is pushing to the right?
Negative one, say again?
Because the negative charge is pulling the particle to the right, and then the positive charge is pushing it to the right. So would you add 4,500?
Well,
I mean, technically.
let me look, Stash. Hold on. Let me go over what you asked me.
Disagree with
Stash.
The field produced, what Stash is saying is the field produced
due to Einstein's theory. I don't really think this is funny.
I don't know. Let me think for a sec, Stash. That might be a valid point. Let's see.
He usually comes in here with the comments.
Wait, where's NECE2?
You guys thought it was.
Both forces are acting.
Both fields are produced to the right.
No, I thought you wasn't.
I do love it.
Yeah, that's a good point you're making there, Stash.
It's not like I've
Guys, for now, put a question mark here. I need to look into this, but I think Stash is right. Because what we're happening here, listen, what we have here in the middle is one field produced by the positive charge, which is pushing to the right. The field from the negative charge is pulling to the right. So they're both together. They're both acting toward the right. So what he's saying, and it is a valid point, I have to look at this, look at my notes, because I might have made a typo here. What we have to look at is the fact that we have E1 and E2 both acting to the right. They're both pushing to the right in this middle point here. So what we might need to do is take the absolute value of this quantity and add together, was it 6750, Fernando?
6,150. It's very messy.
But don't electric fields have vectors? It's like
And that's why I think what you're saying is true, Stash, because of the fact that they're a vector field. So let's write down a little question mark here, and I'm going to resolve this in our next class. But for now, put down this next answer. You get, what is that, 10,000, 11,250? Okay. Let's write down this bottom answer here. I think this is correct. I think what Stash is saying does make sense. Let me look at the electric field and a vector. Okay. Write down 11,250 here, please. Stash, good point. Thank you.
Hey, thanks, man. I found it in my dad's drawer. So.
Now,
Thank him for it.
the direction of this charge, we should write down the direction of it. Remember, if we go back to our diagram, okay, if I go back to my diagram real quick, take a look at the top up here. The positive producing sphere always produces fields outward. The negative producing sphere always produces inward. So what we have is a field going from the positive to the negative charge. So if we're going to talk about the direction here, okay, we can say that this field is from the positive to the negative charge, which gives us the direction of the field lines produced. And that's where what Stash is saying makes sense when we look at the directionals when it comes to the fields. Okay?
But it still is attraction.
Well, this is not, remember, we're not looking at a force, Jeff. When it's a force, we could say it's attractive or repulsive. But this is a field. The field is going from one location to another. It's not attractive nor repulsive. Okay, again, only the force can be classified as attractive or repulsive.
We're trying to figure out.
Field.
No, we're trying to figure out that the negative circle is having that field force attracting that amount of newtons or that amount of force.
But it's not a force. Again, look at your units, Jeff. It's newtons per coulomb. This is not a force. This is a field. It's called a gradient, really. It's the measure at which the field strength is compared to some charge.
So the force is strength.
Yeah. So the field strength is what you're measuring. The field strength. Okay. It's a rating of the
But
force.
going from the positive to the
Correct. That's what you can say. The field direction is from the positive to the negative charge, which means that anything along that field will move in that direction. Paul.
So from the positive to negative charges, that's the 11.
Yeah, 11, 250. Cross off the other one up here. This is one that we were just talking about, guys.
So
Okay?
you're wrong.
We're looking at the absolute value.
So you're wrong.
You enjoy saying that?
Yeah.
Okay, good for you. Now, let's take a look at the homework. Make sure you write down the homework, please. Page 647, number 3, and 652, number 1.